It's a basic Just Give setup, and the idea is to raise funding and awareness for Bloodwise and Anthony Nolan.
I actually had a quick read of some of the poems that you've got on your website, and I have to say, I'm amazed. Anybody who can write poetry is amazing. So.
Oh, thank you. No, it's just a nice project to be involved in, and actually doing these video logs with the charities has been fascinating. Really, really amazing, and above all, actually gives me as a patient lots of hope. Because you just realise how much research and thought is going into improving lives and outcomes for people with blood cancer, and actually it's happening at a quicker pace, whereas previously there would be such a lag time between development and trial and then final sort of bedside, as it were.
I know. I think the transition from bed to bedside is definitely getting shorter, and I think that's because of being more ambitious in trying to get to the clinic. I think amongst the academic scientific community, the idea of translating what you do into something you are going to put into patients is actually quite a scary thought, really, because up until that point it's just something you're doing in the lab. You're effectively messing around in the lab, and it's the idea that you're then going to take this idea and put it into a patient.
Yes.
Is absolutely petrifying.
Is it?
It is, because you think, what if it doesn't work? What if it has some nasty side effects?
Or knock-on effects in other.
It's a huge responsibility, actually.
It is, and I think it's not something that we should be shirking away from. I think ultimately you just have to take a leap, and that means that you do absolutely everything that you can with respect to doing all the safety monitoring that you can in the laboratory, and then just say, you know what, we're just going to have to take a leap of faith and try it. And Chris was mentioning the fact that we generally start the clinical trials in sort of the very late stage patients, and the reason for that is because for those patients there's really not a lot left, and so often they are far more open to the idea that there is a possibility that there may be something that will cure. They also generally tend to be harder to treat because, of course, usually they're already heavily pre-treated to that point. But I think if we consider even the patients who haven't been heavily pre-treated, there are groups of patients for whom what we would say they are of a sort of an urgent clinical need, in the sense that we don't have good therapies for them. So, I mean, you're relatively young to have developed cancer, but in most cases blood cancers and many cancers occur in people as they get older, and it is, in some respects, it is an effect of aging. It is an effect of aging. So it's a cumulative effect of every cell division that happens in our body, what we've eaten, what we have drunk, whether we've smoked or not smoked, any environmental pollutants that we've been exposed to, and so the net effect of that is the risk that you may develop cancer. And obviously the longer you live, the greater your chance of developing cancer. So if you look at the graphs of incidence of when cancers occur, especially amongst the blood cancers, most of them are sort of over 50, 60 years of age. And so, especially when you start looking at patients who are over 70 years of age at presentation, for many of them, intensive chemotherapy is not an option. So from the very beginning, your age is against you. And so what we're saying in those cases is that we are either going to offer you suboptimal therapy, which we know is non-curative, or we're going to offer you palliative care. That's not really something you want to hear, And then you have the other side of the coin, which is the paediatric side, which is that you have children who we get very high cure rates in, but for whom the toxicities mean that they have an impact on the rest of their lives. There are obviously cancers which we're currently not curing, which we need to get better therapies for. And then another aspect, which for me is sort of quite an important one, just as important as those, is that those people who live in low middle income countries, what we used to call developing countries, who just can't afford the drugs. You know, there's huge swathes of populations who we can't cure because we just haven't got the resources and the money and the drugs available to cure them. So what do we offer those people? So there are these areas of absolute utter need, clinical need, that is not always necessarily prioritised by sort of large companies because the financial returns are relatively small. However, that doesn't mean necessarily that the pharmaceutical companies ignore them. It's just that, we try and work hard to convince them that those are some of the diseases that we want to work in. But drug repurposing has a real power here.
Yes, in the developing countries.
In developing, but not just in developing, for example, in our elderly population. Yes. So bezafibrate and Provera, one's used for regulating cholesterol, one's used as a contraceptive pill. Yeah. At the lower doses, the side effects are very well tolerated. They're very low. And the key thing is that especially in the leukemia patients, they do not suppress your immune system, which is the very last thing you need when you are already suppressed because of your leukemia. And so in those patients, we need what we call myeloablative, i.e. they don't damage your immune system drugs, but still effective.
Yes.
And so that's why BAP therapy, we think and believe, is going to have some clinical potency in those patients. But also, these drugs are very cheap.
Yeah.
Bezafibrate has been off license, off patent for many, many, many years.
Yeah.
It's a generic, effectively. If anything, it's getting harder to get hold of because everybody takes statins. But Provera is still marketed, so you can get hold of Provera. But what we decided to do was we thought, well, if these two drugs have anti-leukemic activity and anti-lymphoma activity, how many other drugs do? So we started screening. Yeah. We sort of we literally read the BNF, I did, and it's up here, the version that I read, which is up here. So this is something you must know very well. I do, this is usually, it's electronically in the GP's office, but I literally read one of these from cover to cover and picked out 100 drugs.
Goodness.
And I did read it, I tell you. It was a great read. It really helped me sleep. And we picked out 100 drugs from here. And the reason we did that was we thought we want to just, in a very non-biased way, pick drugs from every section. And where there were multiple derivatives, we tried to go for the cheapest. And especially the oral ones. Because, needles are not nice for anybody, but if you can have a drug that you could take at home, that would be fantastic. Yeah. And also for children, children don't like needles, and if you're dealing with children, especially in low middle income countries, the cost of an IV or a cannula, that gets very expensive. So let's think about oral drugs. So we put together a library of 100 of these, and we started just screening them against all of our cells and saying which of these have anti-tumour activity either alone or in combination. And so we started looking for combinations against all the various different disease models that we had in the lab, and we got a combination that worked very well in myeloma. And the combination, as you mentioned before, is an anti-epileptic, which is currently hitting the news because it's because of the potential side effects on the genetics of children who've taken it and women who may have taken it. But a second,
this is sodium valproate.
It's valproate. And the second drug is niclosamide, which is used to treat tapeworms. But niclosamide, interestingly, if you look through the literature, there are many tumours against which it seems to have anti-tumour activity.
Gosh.
So how do we harness that? So we've been doing all kinds of experiments in the lab to try and understand how is it doing it and why is it doing it. And we think we've kind of cracked it. So we're very close to finishing up the study now and getting it published. But obviously the next step is to go into patients.
Yeah, that's exciting.
With these two drugs, exactly.
Very exciting.
And how long would it take from there? So once you've published the work, just to give kind of people some idea of you've found something, you think, then that further process, kind of the life of it, what happens then?
Yeah. So I think what we're doing is we're being really cautious. We've done a lot of tests against healthy normal cells, because what we want to know is that the combination doesn't have lots of horrible toxic side effects. If we think about it, these are two drugs which have been used for donkey's years.
Yes.
Now, just through serendipity, somebody out there must have used it as a combination, and we've not had a reported toxic effect with them.
Yeah.
The other key difference with what we've been doing is that we always try and screen the drugs at the doses that we already know are clinically safe.
Yes.
So we're not trying to use these drugs at much higher doses, and we learnt that from our experience with the BAP study.
Yeah.
So the next phase for us would be, I think, we would start with a small toxicity study in a small group of patients who are going to fall in that relapsed, refractory sort of end-stage disease patient group, to see, can we combine the two drugs, what are the side effects. The other key thing that we have always done is that if there is a drug that's being used safely in patients, we don't ignore that. So we screen our drugs, these repurposed drugs, alongside those other drugs. So
with it or compared to it?
We've done both.
Oh, okay.
But usually we're looking to combine it. We're looking for adjunctive therapies.
Okay, so attacking it from different pathways and different angles.
So the phrase we like to use is dirty is good.
Okay.
Because the more pathways you hit,
yes,
the less likely the tumour cell is likely to be able to avoid it.
Yeah.
And mutate away and develop resistance.
Yeah.
So dirty is very much good.
Yes.
You know, we know, for example, thalidomide hits many different pathways.
Okay.
It doesn't just hit a single pathway, it hits multiple pathways. So we want to combine it together.
Yeah.
So we have combined it. We've combined it with a drug that is used commonly in myeloma patients, which is bortezomib, and we get significantly better killing when we have the triple together. So we would start off with a pilot study where we just test for toxicity in a small group of patients, and then after that we would move into what we call a sort of a phase 2, where we'd now start looking for effects. Can it improve?
Yeah.
the
Well, it must
patient
be
responses.
just immensely satisfying to go from translating that to then to there, and then finally to the patient.
It is.
But as you say, with it comes the responsibility and the sense of doing no harm either, and trying to tread that fine line between efficacy and side effects.
I think what is acceptable toxicity varies significantly from disease to disease, because the definition of that changes fundamentally.
Yeah.
If you've got somebody who's got eczema and you give them a drug which makes them very drowsy or whatever, they're not going, that will be considered unacceptable.
Yeah.
However, if you have a patient who does have an advanced cancer and you think actually a little bit of drowsiness in this patient is not such a problem whilst they're on treatment, if we manage to get a cure.
Yeah.
So the definition of toxicity and what is generally tolerated by the patients and also the clinicians ultimately as well, which is important because the decision is a joint one, it changes from disease setting to disease setting. But I think ultimately the truth of the matter is that if we never try it in patients, we will never know. Yeah. So you just have to stick your head on the block and give it a go and see what happens. And if it works, fantastic. If it doesn't work, you haven't lost anything. But what we then do is move on to the next project and stop wasting time on researching something which isn't going to make any impact on patient lives.
No, that's very true. I think it's certainly in my situation where options start to run out, you're very much more open and accepting of side effects. So with survival as a benefit, you know, when it comes down to that, then you're prepared to accept a lot more collateral damage, which is probably why you're starting off in refractory and relapsed.
I think it is always easier to set up these studies in those patient groups from the very beginning, because if there is a frontline therapy that we want to use in somebody who isn't in that group, then the ethics there is no ethical reason why you wouldn't offer the person
Yeah.
that frontline therapy, which has demonstrated efficacy in that group.
Yeah.
Unless, of course, if we come back to the original point, that we do find some kind of genetic subgroup which says that this group isn't going to respond to this frontline therapy, and it's better that rather than wasting time on this frontline therapy, we put this group on a novel agent therapy. And so that's where the science comes back in again, is that even with drugs that we do get cures in patients, we rarely get 100% cures.
Yes.
So identifying what is it about those patients who don't respond, can we identify what it is, and then can we then select and screen patients who come in so that if they do have that particular signature, whether it be genetic, whether it be whatever the parameter it is, we send them off rather than wasting time on a therapy that won't work on them. Let's send them onto another therapy that may give them better chances.
Yeah, yeah.
So that's where I tend to call it stratified medicine rather than personalised medicine, because what it's about is saying that, you know, we want to be able to say, actually, this is a signature, using signatures, clever signatures, to really give patients the absolute best chance that we can offer them.
Yes. I mean, as a patient, the other important thing which you also mentioned is toxicity. And it's a funny situation because to begin with, certainly early on in a cancer journey, you don't feel too ill, particularly if you've been diagnosed early. And then you have a whole bunch of treatment which makes you feel ill and causes long-term damage, and actually puts you in a worse situation, you know, in terms of quality of life. So it's a funny paradox where, you know, it's where the treatment actually impacts more on your life in terms of toxicity afterwards than the initial disease. But obviously, you know, without treating the disease, you wouldn't be around. But,
no, absolutely.
But it is a funny sort of thing to get your head round as a patient, and I'm certainly noticing it. You know, particularly with you become a bit more preoccupied with the fact that it's difficult to walk, for example. But actually, you have to remind yourself, at least you're here to walk.
No, exactly. But I think for us as a scientist, and I know for me as a scientist, trying to develop new therapies, is that that's one of the important factors that we always take into consideration is quality of life whilst on treatment, whether it be curative or palliative or whatever it is. It is about the fact that whatever time that you can buy for the patients, it is a good quality of life that you buy for the patients. You know, we always talk about how the clinical goal can be very different from patient groups to patient group. If you have a 75 or an 80-year-old, and if they develop, say, leukemia or myelodysplastic syndrome, and if we believe, which we do believe, and hopefully the clinical trial will prove and demonstrate it, but we need to do it, is that by taking some drugs orally every single day, that we can keep the disease in check and reduce the symptoms, improve the symptoms, and actually potentially even suppress the disease and reduce the level of the disease over time, that these patients could take the tablets and the drugs daily for the rest of their lives, in the same way as you would take your type 2 diabetic medicines or your heart medicine or your cholesterol medicine. You know, in a patient group like that, you could argue that not necessarily aiming for an absolute cure, but making the disease effectively controlled.
Managing a chronic condition.
Yeah, it's turning the cancer into a chronic condition in that group may be potentially an option that we ought to be considering. Because you're buying quality of life whilst on treatment. Whereas, and ultimately you want to go for cure. You always do. But the second option would be this sort of chronic disease which is managed and the side effects are minimal. Children, on the other hand, though, you have to cure. Because what you have to do is cure them in such a way that you buy them a long lifespan of healthy life with minimal side effects of their disease, you know, from the treatment. and the challenge is very different there. So there you have to definitely eradicate the disease, and you know, and so therefore you may think about being more aggressive about the type of approaches you would consider using.
And they tolerate treatment much better, don't they?
Children are amazing. I mean, I've just come back from a trip to Egypt and to Tanzania, where I basically went to children's hospitals, oncology wards, and met with paediatric oncologists to discuss potential collaborations on sort of how we may be able to help and improve the outcome of children with cancer in these low middle income countries. And when you go into a ward in Tanzania and see these children with these sort of very large advanced tumours, because that's often what happens in these countries in sub-Saharan Africa. Children present with an advanced disease because by the time they have been able to get to hospital, the tumour is well and truly advanced. So it's not uncommon for tumours to be sort of a grade 3, grade 4 when they turn up at hospital. So you're already against it. You're not dealing with early stage disease, and then you can't give them really intensive cytotoxic chemotherapy because that will kill them. There's no supportive. The supportive care is very limited. You know, the idea of having platelet transfusions or neutrophil transfusions or anything like that doesn't exist. You know, we don't have the resources or the money to be able to do that there. So here, in that setting, we need these drugs, which are non-toxic, are going to be curative, but also have to be affordable as well. But I think that question of affordability comes back to the rest of the world as well. The NHS is struggling, as we all know. And we need to tackle the fact that we need therapies which are more affordable than some of the newer drugs that are coming on the market. And our pharmacies are full of drugs that we're finding new uses for all the time. So what we have to do is get organised about finding the new uses for cancers and then getting them into clinic as quickly as we can. And the beauty of using these drugs, which are already in the pharmacies, is that, you know, and our mission is 3 years, is that within the time frame of a 3-year grant from somewhere like Bloodwise, that we would screen, we do all the necessary laboratory work, and we move into clinical trial as rapidly as we possibly can. And that is the mission that we set ourselves. You know, and we've been, over the last few years, we've been getting to a point where we are developing the pipeline, developing the system, getting faster at working through the system, with the view that what we try and do is create a facility where we can just rapidly screen and just come out with hits and get them into clinic as quickly as possible.
And there's quite a close relationship with the clinicians. So at different call faces, you're able to dovetail together.
Absolutely.
Birmingham's a good example of that, isn't it? Because you've got the TAP hub that's based here, but you've also got actually some people who are working on the very basic kind of molecular kind of research to people who are looking at kind of treatments. So you've got that, and it's all here in one place. And it kind of is a community, isn't it?
It's a fantastic community. So having been at this university now for a very long time, what I do know is that the reason why the university is so good at translational research, and what we mean by translational research is doing the basic stuff and then getting it into clinic, is the
bench to bedside.
Is the fact that we have clinicians on our doorstep, we have a large hospital, we have clinicians, we have medical school, we have clinical academics, you know, and the teams work together with basic scientists and chemists and physicists and whatever, and we really can develop an understanding of the language and the need. Now, I came to Mark and Chris 15 years ago, as I said, and before coming here, I was sort of very much a lab scientist. But now, you know, my headset and the questions I ask are very different. You know, it's a case of what is the purpose behind this experiment? How is this going to help us to get into the clinic? And also the parameters that we consider, I consider now, always has the clinic and the patient in mind up front.
Yes.
And it's a very different way of thinking about your science. you change from just thinking, wouldn't it be cool to just try and work out this, to how will understanding this help me to get this drug into clinic better, or design a better combination of this drug to get into clinic. Yeah.
That's the thing that actually surprised me when I started 5 years ago, and it was the thing that surprised me meeting researchers and introducing them to kind of patients, because often we do lab tours with fundraisers who quite often are patients or patients' families, but actually how interested they were in the patients, how considerate they were about the effects of what they were doing. It didn't feel like there was a disconnect. It feels like there's a definite connection between the lab work and the impact that has, and how they want to connect that to people.
It's joined up research, isn't it?
It is.
And as a patient, that's sort of music to my ears, because rather than thinking, you're in your silos, maybe just trying to find out the mechanism of an obscure pathway, and this is actually impacting directly to our well-being.
Yeah. I think you need both. You need to have the silos, and I think the reason for that is that the silos, those people just working on a pathway in a model system in the laboratory, identifies the aspects of the basic biology that we wouldn't necessarily dedicate that much time to.
Yes.
So when we get a hit, we would go and look in the literature and say, what do we know about this? And those silos, those people who are doing that basic research, that gives us the information we need. We exploit that information. We also do a lot of basic research ourselves, trying to understand what the drugs are doing, because we also know that drugs have what we call on-target effects, i.e. the things that the drugs are known to do. They also have off-target effects, and these are the effects that are unknown to us, and we don't understand the importance or relevance of them with respect to the activity of the drugs. So, and that gets more complicated when you put drugs together.
Yes.
When you start putting combinations of 2 or 3 drugs together, it gets very complicated. And then you start seeing pathways being modulated that you never saw with either drug alone.
Yes.
And so you have to have a very open mind about the pathways that you're going to see being modulated inside the tumour cells. But I think, ultimately, you have to have a full spectrum. You have the pure clinician sitting over there who only ever really sits and talks to patients. And over here you've got the blue skies scientist who really will never meet a patient, will never go into hospital, but will sit there and cogitate and come up with some fantastic ideas and breakthroughs about basic biology of what's going on. And then you need this spectrum in between of people who sit and can translate between the two. And it is important, translation, because language is a barrier. Clinical language can be scary to a basic scientist. The clinical language will sound scary to a patient who's a non-clinician. For example, you're a clinician, so you will be more familiar to you, but even some of the terms used by the oncologists will be new to you, the hematologist. Likewise, for a scientist to hear the phrases from the clinicians, that's scary. And vice versa. Because, I've been in meetings where I said, wouldn't it be great, this is early doors. I said, well, wouldn't it be great if we did this? And they were like, well, how's that going to help the patient? We would never dream of putting this in a patient, so why are we going to waste time on this? And then you think, oh, okay, all right. And it's the process of communication, by constantly communicating with each other and having all sort of parties effectively part of the development process. You really kind of get to where you want to get to, which is drugs in clinic and patient benefit.
There's a sort of common outcome and purpose, and so that galvanizes the direction, doesn't it? In the way you can then put together a piece of work.
So, and I think there's that mutual respect as well, isn't there? It's not that one part of that process is more important than the other part. Investment needs to happen at all places, because otherwise, if you slow up on one point, then actually it impacts later on down the line. So I think the thing, as I would say, is the majority of our researchers kind of have a bit of a, love of the other people who support them in that kind of journey. There's a recognition, I guess.
But even from scientist to scientist, not even clinician. If I'm talking to my colleague and friend who works in nuclear magnetic resonance, he'll talk a language that I don't necessarily understand. And I talk a language that he may not necessarily understand. But what we have to do is work away through the barrier of language and get to a point where we have a mutual understanding about what we're trying to do. What is it that the results mean, and how can we interpret and do something useful with the results that we get. But this is a process. I think the more you talk to people, the easier it becomes, and also the better we get at explaining ourselves. We always refer to lay language in the sense that how do you explain a complex problem, and I'm sure you've encountered this as a clinician talking to your patients. How do you explain what you're doing in sort of this scientific way, but in a language which somebody who's a non-scientist can actually understand it and comprehend it? And not misinterpret it, because that's the challenge, is not misinterpreting what you're saying. We're not promising cures, we are aiming for cures, but we can't promise them until we've done all the work.
It's about defining expectations, and
Absolutely.
I think that's very important as a patient to know where you stand, and I think it just gives me great heart actually to listen to this process and actually engage with it much more as a patient and as a fundraiser, because you actually become aware of everyone pulling together in the same direction.
And as a fundraiser, you're part of that.
Yes.
It's not a disconnect to it. It's actually
as a patient as well. So you feel part of a process, and it's quite. It's great, and I feel very. I don't know.
Oh, we've got a use for you now, haven't we?
Thank you, Joyce.
But I think also, what I will say as a scientist who's been funded by Bloodwise now for many years, is that as a charity, Bloodwise has had a very patient focus, a very strong translational focus in what they want to fund. That is fantastic, because what it does mean is that sometimes when you're doing very translational research, it's not always the sexiest research. It's not sort of the most exciting in the sense of new technologies and things that you're doing, but it's some of that research is more relevant in terms of getting into the patient.
And to what extent have you able to do research in other types of cancer? How applicable is the science that you've done in blood cancers? How are they applicable to other types of cancer?
I'll pay you later, Jay. You've set me up nicely there. So this whole idea of screening available drugs in combinations or as adjunctive therapies, we're now testing it in. We're doing it in blood cancer, we're doing it in head and neck cancer, we're doing it in ovarian cancer, we're doing it in a whole range of cancers. We're looking in infectious diseases, not just of humans, but also in camels. It's important. It's important.
Oh, careful! Yes.
Camels are a major agricultural industry in Egypt. So there are infections that are becoming resistant. So, we shouldn't restrict our thinking.
No.
But you're right. This platform that we are using does have a massive scope, just way beyond what we're looking at in just blood cancers. It goes beyond everything, and it could go into rheumatoid arthritis or anything. So the whole concept of drug repurposing has gained a huge momentum amongst the academic community, and we've been doing it Mark and Chris have been doing it for 25 years. I've been doing it for the last 15 years, way before it was trendy and everybody wanted to do it. But I think it does have a huge power behind it, because what it means is that we can go from that lab finding into the clinic so much faster. And not just that, you would sit with a clinician and the clinician would say, you can't have that drug in this patient because that drug causes this side effect and these patients can't tolerate it anyway, so there's no point you screening with those drugs. You've got to have this drug. And it's brilliant. That's the frankness of the conversations that you have with clinicians. So And what we're trying to do is not just focus on Birmingham as well. We want to take the whole repurposing, if you like, toolbox and make it accessible to anybody who wants to do it in the academic community.
Yes.
So we have big plans for creating a national facility to try and be able to do that.
Yes.
But we need obviously to work on funding and develop the project.
And I think the fact that actually the research can benefit so many other groups will also engage a wider community to perhaps donate or get engaged with the work you're doing.
Yeah. Well, we hope so. I mean, we're trying very hard, and I think it's a case of watch this space. We'll hopefully later this year come out with some more information about what we're trying to set up. But in the meantime, we're pushing on with the various different drug combinations that we've got in the lab. So we have a combination for myeloma, which is really well developed. We've got a combination for bladder cancer, which we really would like to get into clinical trial at some point later this year. We've got another combination for Burkitt's lymphoma, which is this lymphoma that affects children in sub-Saharan Africa, which we hope to take into early phase clinical trial once we've done some more laboratory experiments. And then there's others as well. So it's a pipeline. We have to view it as a pipeline, and it has to be a case of we have to just keep screening and churning and getting all the necessary data and getting it into clinic as quickly as we can.
And the other thing actually which occurred to me whilst talking to you is the ethical face of something like that. When you talk about going to sub-Saharan Africa or whatever it is, at a time when charities are going through a tough time in terms of ethics, and industry always has a bad, can have a bad face, all going for profit and expensive treatments, and by sort of having an ethical face, I think is very important as well.
I mean, this is where I'm going to step. I mean, yes, the pharmaceutical industry often does have a bad reputation because, they're often presented or at least seen as being money grabbing and charging huge amounts of money for a drug. Now, I would actually say that's not true at all, because ultimately it comes down to basic economics. They are a company, they are responsible to their shareholders, they have to make a profit. And ultimately, they have to make a profit to be sustainable, to be able to continue to manufacture the drugs that they make. Now, if you have a drug for a condition which is chronic and that there are millions and millions and millions of patients out there, then you can afford to charge not so much for the drug and still get a profit back. The average cost of developing a drug is now estimated at $2.5 billion.
Wow.
That's huge.
It's massive.
So the numbers vary somewhere between 1.5 billion up to about 2.5 billion, depending upon whose report you read. But let's say it's $2 billion. A company has invested that, and somehow or other they need to recoup that money back. So you can understand why, if you have a drug for a cancer which doesn't affect millions of people, the cost per patient will be more expensive. And so it comes down to basic economics. They're not the bad guys. Ultimately, they are creating medicines that are hopefully going to be curative. What we do want to do, and we are doing, is we're trying to work together with the pharmaceutical industry to say, what we'd like to do is take some of those drugs that you have in your back catalogues and screen them for new uses and find repurposing opportunities for them. And sort of rather than working against the companies, let's work with the companies. And many of the companies actually have come on board with this repurposing process because they have made some of these compounds available to academics for screening, and you can apply through various different schemes to screen.
There are additional indications for them, so it's they win.
But isn't it as well for the trial acceleration program? Quite a lot. Some of the drugs are donated by the companies because it reduces costs for them, and we want to reduce costs for them because then it actually takes it off that end price for the patient.
Yes.
So by working with them rather than kind of buffing against them, it kind of
Absolutely.
it helps the end result. So.
And then the ethics of working in low middle income countries in sub-Saharan Africa and in very vulnerable groups like children, etc. You're dealing with often a non-literate population. You know, the ethics absolutely have to be 100% on point, because you cannot and will not, should not be doing any study which is taking advantage of the patients out there. You know, and it isn't just about using the populations in sub-Saharan Africa to develop a treatment which we want to use here.
Yes, not experimenting.
Absolutely, absolutely zero, no way.
Yeah.
That is
Yeah.
not acceptable in
No.
anybody's book.
No.
We are interested in trying to find these drugs, treatments, which can actually are curative in the settings that the clinicians have to work with in those places. And if you do go into a hospital in these places, in sub-Saharan Africa or even in North Africa, you realise the conditions are very different from here. And it's a real eye-opener. You know, you really will see things that you would never expect that you would see. But it's important that you see it, because that's the challenge that the clinicians face. And so what's good to know is that all of the studies, especially the clinical trials that people try to do, have to go through a very strict, rigorous ethical review. And often there is a committee which is made up of international members whose job effectively is to almost act as parental. They are able to consider all the evidence and be absolutely sure that what you are doing is in the best interest of the patients, and provide the information in a way that is going to be made clear to the patients who are going to be potentially signing up to a trial. But ultimately the trial is not the end goal. The trial is the stepping stone to getting a therapy into routine use.
Your motto is?
Make a difference.
Make a difference.
and I have to say, you know, as a patient meeting a researcher and a scientist at the coalface, it's been eye-opening. It really has, to understand your motivations, the way you work, and it gives me great heart, as I say, you know, to know that everyone is pulling together in the same direction for us.
We absolutely are. We absolutely are, and I think ultimately we just have to we keep aiming and trying, and we will make progress gradually. And I think, you know, what we want to do is get to the point where no patient ever has to hear the words, "I'm sorry, there's nothing more we can do for you." That's the mission.
Shows the bench to bedside, isn't it?
Yeah, so this is what we're trying to effectively do. What we do is this bit, which is the screening, the validation, and that happens in the lab over there, and then we go into that early phase study, and then really what we want is a happy dancing patient at the end who's cured and ready to get on with life and not have to worry about that word again. So this is the motto we work to. It's going to be really good for you to be able to actually see what these tumour cells look like.
That will be really interesting.
We grow them in the lab and actually do stuff to them, try and kill them in the lab.
Good, yes.
So in a nutshell, there's nothing very clever. We're trying to
So we are actually culturing a whole range of different blood cancers and bladder cancers and various things. This is Brother, who's a PhD student in my lab. Brother?
Hello.
Brother is actually working on Burkitt's lymphoma, which is a lymphoma that affects the children in sub-Saharan Africa. So we have a theory about what we think may actually even be causing the cancer to develop at such a high rate in those children. And Brother is actually is testing that as part of his PhD program.
Very interesting.
It is. But also testing the treatment options that we've got as well, which is another repurposed combination. Thanks, Brother. Right, let's get some cells. There you go. which is basically a solution of amino acids, nutrients that keeps the cells alive. We put supplements in it and it keeps the cells nice and happy. We do tend to grow them in a very artificial condition, which is this little plastic container. We keep them sterile. The reason and there's a little filter in here which allows oxygen and carbon dioxide in and out, but doesn't obviously let any bacteria or anything else get in here. Half of the challenge when you work with these types of cells is to actually keep them free of bacteria and yeast and things, because if that happens, you have to throw them away. So a lot of the work we do with these is all about keeping them safe. Sterile and safe. Now, handling the outside of these, there's no dangers associated with it because there's nothing on the outside of these. So what I've got here for you are these are two cell lines, we call them, established from two different myeloma patients.
Yeah.
And these were established from leukemia patients.
Yeah.
Now, I don't have any T-cell leukemias growing, but what we do have is a range of myeloid leukemias. So this one here has got the Philadelphia chromosome mutation that we talked about earlier.
Yeah.
So I'm just going to get it into the right focal plane for you, and then you can have a look. Okay. So there you go. So those little white balls, which is what you're going to see down there, you may need to focus. I have very funny eyes.
No, I can see them. Yeah, so they're sort of very quite homogeneous, aren't they?
Yeah.
They're sort of similar looking cells, and then
they're small round. In some places you can see two cells which are sort of very close to each other like that, almost like they're glued together.
Dividing cells.
Absolutely. So those are cells which have just divided.
So these are living cells?
Yes.
Wow.
Those are growing tumour cells.
Yeah.
So what we effectively try to do is put drugs on them and try and stop them dividing and either kill them or differentiate them, and they die.
Yeah.
And that's the mission of what we try and do. But importantly, as a tool, they're very powerful because they do allow us to do experiments that we can't do on human beings. You know, we sometimes can get primary cells from patients and do the experiments in the lab with those.
Okay.
But you rarely get enough cells to be able to do a lot of experiments with. These we can grow up to litres of these if we need large numbers of cells.
Yeah.
But if we, say, have a bone marrow aspirate or a blood sample from somebody, then it's quite hard to get a large number of cells, you know, in those cases. So what we do is and there are different culture conditions. There are different ways of growing the tumour cells that can allow you to expand and maintain what we call primary cells straight out of a patient in one of these incubators.
Yeah.
They are the ideal cells ultimately because they're the cells that, you know, are fresh. These are abnormal. Not every tumour biopsy that we get will grow in the lab and establish a cell line.
Okay.
So there is something a little bit anecdotal about these. Absolutely.
Yeah, but it's still a good model.
Absolutely.
For what you're trying to achieve.
They are a very good model, and many treatments that have made it to clinic were developed testing using cell lines similar to this.
Yeah.
But importantly, you do the studies on here, and then you would go back and validate against primary cells.
Yeah. Okay. Yeah,
you'd always look at the
patient
primary,
itself.
exactly.
Yeah.
Always validate it.
Yeah.
And there are other model systems that people are developing, sort of 3D culture systems, organoids. The reason for that is really quite important, and the reason is tumour cells don't grow in isolation. Tumour cells grow within the context of a complex environment within our bodies, and that complex environment is constantly talking to the tumour cells. The tumours are talking to the environment. Importantly, the tumour is getting nutrients and essential factors that it requires to grow and proliferate. Often the way the tumour will do that is by modifying its environment. So sometimes some of our anti-tumour activity can occur not because we target the tumour cell directly, but because we target what we call the niche, the environment that the tumour is trying to grow in.
Yeah.
And so a good example of the fact is that there's the seed in the soil. You know, if you have a seed, you can't necessarily get a seed to grow unless you put it in the right nutritional environment.
Yeah. Yeah.
Same goes for a tumour.
Yeah.
It has to have a permissive environment to grow in.
And sort of things like sanctuary sites.
Absolutely.
Where cells can take refuge, be dormant.
Yeah. So CLL, chronic lymphocytic leukemia, is a really interesting disease from the angle that it has sort of at least two major compartments, the blood and lymph nodes. In the blood, the tumour cells are non-dividing and they're relatively sensitive to chemotherapy drugs. In the bone marrow, in the lymph nodes where the tumour cells are, they are protected by an environment, which means that often they're drug resistant, and also they proliferate in this niche.
Yeah.
So they grow, and you get the massive proliferation that you see, and you see the lymph, the large enlarged lymph nodes, and so to really cure somebody with chronic lymphocytic leukemia, you not only need to wipe out and eradicate everything in the peripheral blood, you need to kill everything that's in the lymph node as well.
Yeah.
And that is true obviously for any cancer.
Yeah.
You have to get rid of all the cells.
Yeah.
Or indeed, get those cells into such a deep state of sleep that they don't proliferate and grow.
Okay, switch them off.
Switch them off.
Yeah.
So create a non-permissive environment for them.
Yeah. Complicated, but fascinating.
And very interesting, isn't it?
Yeah.
This is really good.
But also to get them to that stage is quite a long...
Oh, to grow cell lines is not easy. I mean, it's not every day that you can grow a cell line. It takes a lot of work to grow a cell line. I'm going to put these back just because it's actually quite a cold day, and these like to be at 37 degrees.
This is their cosy place.
Yes, so what we do is this is at 37 degrees Celsius, and it is warm and it's humid. So the humidity stops the evaporation, because of course if you put anything in a warm environment you get evaporation. Humidity stops the evaporation or limits it, and we keep everything at 37. Not just that, we keep it at, we regulate the carbon dioxide levels in there so that it's at 5% carbon dioxide, and what that maintains is the right pH balance for the cells that they're growing in, and that keeps them really happy. Until we kill them, of course, with drug.
One thing I've noticed, Jaya, she smiles every time she says kill them.
Slightly psychotic.
Good, dead.
Slightly psychotic, yeah, no. Well, this is, literally, it's really simple. We're trying to kill the little buggers, and actually we do what we have to. So, it is, but we work backwards. So what's interesting is there are people who try and identify the really important mechanistic changes and then find targeted drugs that hit those changes. We go the other way. We say, we'll screen the drugs, we see the drugs that kill, and then we figure out how they work, rather than going the other way.
And is that quicker? Is that what you do it because it's quicker?
Yes.
And it's tried and tested anyway, isn't it?
The drugs are tried and tested. We already know what the toxicity profile is in patients. We know who can take it, who can't. We know how much you can take safely. We also often know don't take it with this drug, and you can take it safely with another drug. And then we we work backwards. We look for the kill, and then we work out how they work. And then we try and use rational science approaches to say, if this is what the drugs are doing, can we combine it with something that may add to that effect to give a better kill? So it all comes back down to killing.
Good. Yeah. No, thank you ever so much. It's been fascinating. You guys are amazing.
I feel like cheering, don't you?
Yeah,
Well, don't you? Yeah.
Thank you
Well,
so
we
much.
actually get. We have a huge number of projects at the stages where we are almost ready to go into clinical trial.
Yeah.
And it's only really when we prove efficacy in the patients that we really want to cheer at that point.
Yeah.
But up until that point, it's just head down and graft.
Still, I think you guys are amazing.
But also, I think it's to make the money you raise. This is where it goes.
I was going to say, this is where your money's going.
That's it.
It's
This is,
tangible.
and actually, you know, it inspires me more, having seen this and learning that the money you raise is going to make a difference. You know, it's helping to make our lives different.
It does.
And our families' lives different.
I think the other thing that we have to not forget in everything that we do is that, especially having worked with tumours that affect sub-Saharan Africa, but even closer to home, there are also big ethnic differences in response rates and things.
Okay,
and we really have to think and consider that when we think about treatments. For transplants, obviously, trying to find a donor.
Yes.
Finding a donor who is matched means going into the right ethnic community.
Exactly.
And I know that that's an area we need to do a lot more work on in raising awareness and recruiting from our ethnic minority groups. But also there are genetic ethnic differences for why we may respond differently to drugs. And we don't yet fully understand all of those differences. And that's an area of a lot of active research by other groups to try and understand that.
And I think that'll be a greater challenge as ethnic diversity increases. And Birmingham's a
gets
good
more
hub.
mixed.
Yes,
it's a real good melting pot.
race,
Exactly.
But then actually by just identifying a few signatures, it may be that you can find out which signatures are important and which are less important, although you have a greater soup.
My ideal scenario is we find a combination or a triple, which it doesn't really matter what your ethnic background or what your genetic profile of your tumour, it will kill it it'll just kill it.
Yeah.
That's the holy grail for me. You know, I'm not sure we'll ever achieve that, but you know, that would be the nicest solution because it's in some respects the most cost effective, but also the most effective for patients. Priority number one. So we'll see what happens. We'll keep you posted on the trials and what happens.
Yeah. And we'll let you know when the video logs come out. And it's been, Joel, I don't know about you guys, but it's just been an amazing tour and interview. Thank you so much.
You're very welcome.
I knew I should have done something more constructive this time.
I don't know, travelling and climbing 47 mountains sounds like a pretty good idea.
We'll swap next time.
Okay. We'll do. I'll give it. I'm game. Even though I'm a bit scared of heights, but I'm game.
Well, they're all little Mount Everests, aren't they? These things.
Yeah.